All right, flexure formula, bending. All right, TA Indy, give the students a big flex. Show them how strong you are. Right up here, flex. Flex for the camera, Indy. Show the students how strong you are. This has to do usually with I-beams, and you're figuring out if you push down on them and they're gonna bend, right? So these are bending problems. What's the maximum bending stress in this beam? All right, maybe TAND doesn't want to do a flex, but maybe we can get him over here and do some bending, right? If I give him some pats, maybe we get a big bending, big arch. What do you think, TAND? You want to give students some bending? Show them. There you go. That's not too bad, right? Nice little arc bending. All right, so start off normal stress, right? It's just F over A. So if our final answer is going to be force, the force in each of these areas, the area is super easy. We just got 5 and 3. So we're really just trying to find stress, find the bending stress. That's going to use the flexure formula, My over I. Now M, this is going to be the bending moment applied to the beam. I is also a constant. It's just based on the area of the beam, right? It's the area moment of inertia. So it's really only Y that is a little bit variable in that Y changes at different parts of the beam, right? It's how far away you are from the neutral axis. Now we're given M from the figure, 15 kip feet. And I want to be a little bit careful here. This is feet, but all of the dimensions I'm given are in inches. So there's going to have to be some unit conversions done at some point in time. Right? If you've ever heard the expression eat the frog, is basically the idea of if you have to do one really bad thing in a day, you might as well just do it first thing in the morning, so then the rest of the day is all uphill from there. So let's eat the frog and just do I, the area moment of inertia. Let's just find that first and get it out of the way, because that's going to be the big annoying math part of this problem. So in order to find I, we can divide this shape, this I-beam, into 3 different rectangles: the top flange, the web in the middle, and the bottom flange. So I is just adding up all 3 of these moment of inertias of each of these 3 rectangles. The I for each individual rectangle, 1/12 BH cubed for the rectangle itself, but that's rotating about its own center of gravity. So plus AD squared, that as a parallel axis theorem term, which is going to be based on the distance from that area to the centroid. Speaking of centroid, we don't know where the centroid is, because the top flange and the bottom flange are different areas. The centroid's not going to be right in the middle. So in order, this is why it's eating the frog. It's like it just keeps going deeper and deeper down the rabbit hole. So all right, now before we can find I, we need to find where the centroid is. So I'll use still my 3 rectangles, and the centroid is a weighted average, sort of like calculating a GPA. We're just going to need the areas of these 3 rectangles and the locations of these 3 rectangles. So I'm going to do all my measurements from the very bottom. So my areas are, let's see, 3, 8, and 5, right? Just based on base times height. And then my distances are 0.5 on the bottom, because it's a thickness of 1. Then 5 up to the middle, which is 1 plus 4. And then 9.5 up to the top, the 1 plus 8 plus an extra 0.5. So for centroid, my numerator is area times distance, and add those up. And then the denominator is just all of the areas. So when you have area times distance divided by area, your answer is a distance, which is the centroid, which is what we're looking for. So 5.56 inches is Y bar. So the centroid is 5.56 up from the bottom. Now we can do moment of inertia, finally. So we've got 1/12 BH cubed. B, base, is always the width. H, height. So the flanges have a very wide base, very small height. The web in the middle, very narrow base, taller height. And then D is an AD squared for the parallel axis theorem. D is going to be that height to the centroid, so like 9.5, minus the 5.56, the location of the centroid, right? Height minus centroid gives the gap, the distance to the centroid. All right, so we plug in a whole million numbers here, do a bunch of calculator work, 200.28 inches to the fourth for the moment of inertia. All right, so now we can find force is stress times area, my over I times the area, so the 15 that was given. Now, y, in this case, is going to be the distance from the centroid. So if I'm calculating force on the top flange, I'm going to calculate to the center of the top flange. So my y is going to be from the center of the top flange to the centroid. So 9.5 minus the 5.6. And we divide by the 200 for I, do some unit conversions here and some calculator work. We get to 17,700 pounds, 17.7 kips if you would prefer that. And for the bottom flange, we still have the same moment, which I'll just go ahead and write in this time as like 180,000 since I've already done the unit conversion. The distance, that 5.56 minus 0.5, the distance from the centroid down to the center of the bottom flange. And of course, multiplying by the area, 13,600 pounds is the total force on the bottom flange. And if we want to find the maximum bending stress, so the maximum bending stress, if we look at some different points, so if I number points on my figure, 1, 2, 3, and 4, 1 is the very top, 2 is the center of the top flange, 3 the center of the bottom flange, 4 at the very bottom, the maximum bending stress will either be at the very top or the very bottom, because the moment is the same everywhere. The moment of inertia is the same everywhere. The only variable that changes is y. Y gets larger the further away from the neutral axis you get, the further away from the centroid. So it'll either be very top or very bottom. And since we already know that the centroid is closer to the top because there's more area on the top, we can already predict that the maximum bending stress is going to be at the very bottom. But I'll go ahead and write them both out just so that you can kind of see. And so M is the same, I is the same, but what's different is Y. So we have 10 minus 5.6 in the numerator for stress at 1. But for the stress at 0.4, we have 5.56 minus 0, right? There's a distance on the top of only 4.3 and a distance on the bottom of 5.6. So we know that theta sigma 4, the stress, max bending stress on the bottom is going to be larger. So we can actually do the calculator work here and get 5,000 psi as the maximum bending stress, which you could call 5.0 ksi, max bending stress for this I-beam. If this video helped you out a little bit, you want to help me out a little bit, go ahead and hit the subscribe button. I know it's a stupid vanity metric and subscribers don't mean anything, but I still love seeing that number tick up a little bit higher every day. So I would really appreciate it. And good luck on your next test. I hope you do awesome.